Now let's talk about the general idea that posed through the history of science in terms of space, its absoluteness, and finally the motions in this space. And if we go back uh, to the Newtonian mechanics and what Newton insisted, uh, he insisted on the existence of the absolute space. So, so Newton insisted that there is something what's called as absolute space and absolute time. Not only space is absolute, uh, as per him, the time is also absolute. Now, the absolute space was considered to be a fundamental frame of reference in which Newton's laws of motion were thought to be strictly valid, and the deductions, the derivations based on the Newtonian concepts, they did not go against our common experience, against our common sense, and 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 that's why they became elements of our common sense. And for more than 2 years, the equations of motions that were stated by Newton, they were believed to be perfect. They were believed to be perfect in describing the natural events or the natural phenomena. So we can say that in Newtonian world we have constancy of mass. I mean, mass is constant, and the equation that we have, F is equal to ma, it was not doubted by anyone. And then in 1905, Albert Einstein posed a challenge to Newtonian concept of space and time. And he straightforwardly demolished the concept of absolute space. Absolute space. He demolished this idea and time. And what he did, he gave a new idea, and that new idea was relativity. It was relativity of space and time. Now, Einstein's theory of relativity dealt with the same blow as Newtonian classical physics, as Newton had done to the age-old Aristotelian idea of motion. And in this case, what was done that in Einstein's case, what was done, the Galilean transformation equations, they are transformed. They are basically not transformed; they are replaced by Lorentz transformation equations, and the classical laws of addition of velocities when it comes to the speed of light, they had to be modified. Like c plus v is only c, and c minus v is only c. And this became possible when physicists tried to extend the common sense that was purely with Newtonian mechanics to the fast-moving objects that are moving with the speeds that are close to the speed of light. I hope everybody is fine, and in this video I'll start the new series of videos based on relativistic motion, and more probably I'll be talking about special theory of relativity. But before going into the details of special theory of relativity, which was which was proposed by Albert Einstein. And let's talk about Galilean transformation equations. And what we have is if we have two frames of reference, say for example, this is a frame S, and there is another frame of reference S dash, and and what is important here is that we can see that we have a relative motion, and what's assumed in this kind of motion is that the frame S dash is moving with constant velocity. It's moving with constant velocity uh, uh, relative to the inertial frame S. And this S itself is an inertial frame of reference, and we better understand that inertial frame of references, or those frames of references in which Newton's laws hold. So if I assume this motion is along x and x along x, so if I choose it like this, so this will be my x dash, and this much of separation will be vt. Now time is absolute in this formalism, and so if this is x dash, this is my x, and then we can choose a coordinate. Say I have a coordinate, and this coordinate is p, and this coordinate has it has coordinates with respect to S dash. Its coordinates are x dash, y dash, and z dash, and t can be the time chosen as a coordinate. Not a coordinate here. T is the time for which this frame of reference is moving, and there's no difference between the time over here and the time over here. So what's going to happen is that if we see this point P, it is at distance x with respect to this S frame of reference. So it's at distance x, and so the case is very, very simple here. So what we have is we can talk about, or I'll take a position, or that r is that r dash is going to be r minus vt. Okay, so that should be the case. So this r is r dash is r minus vt. Now choosing for x will give me x dash is equal to x minus vt. And since there's no motion along y, so y dash will be equal to y, and z dash will be equal to z. So these equations that we have, they are a representative of Galilean transformation equations. And these equations they give us a simple transformation of coordinates from one inertial frame of reference, say from S to S dash, or S dash to S. So this set of equations that we have here, we call them as Galilean transformation equations. So this was the original choice, but the motion is only along x. So this x dash is simply x minus this much of distance, and there's no motion along y, so y dash is equal to y, and z dash is equal to z, and for t dash is equal to t, because time is absolute, whatever the case is in case of Galilean transformation equations. So we can write down here inverse Galilean transformation equations. So for inverse, we will have x is equal to x dash plus vt, and for y I will have y dash, for z I will have z dash, for t dash I will have t. So the velocity, if we have to talk about the velocity transformation in Galilean transformation equations, we can have velocity transformation equation. If we take the original equation R, R is equal to R dash plus Vt. What we can do is we can differentiate with respect to time. So what we'll get, dr by dt is dr dash by dt plus vt t by dt. So this dr by dt, let's assume that this is the velocity along 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 x, or take the general velocity, say u. So this is u is equal to some u dash plus this u is equal to some u dash plus v. So what we see here is that we have the velocity transformation equation. So if you want to calculate the velocity of an object from say from s dash, we can have a transformation of calculating the velocity in any of the two frame of references. And similarly, we can have the acceleration. So if we want to have acceleration, and for acceleration transformation, what we will do, we will differentiate this. We will differentiate this equation again. This equation we will differentiate again. So when we differentiate this equation, what we'll get is du by dt plus equals du dash by dt plus. Now this v is constant, so its derivative will be equal to 0. So what we will have here is we will have the transformation of acceleration. So what we found here that the acceleration measured on both the frame of references, whether you measure the acceleration from this frame of reference or you measure the acceleration from this frame of reference, it's going to be same. Its value is same. You have the same acceleration. So now if we go a step further, like when the velocity if we like to see the velocity transformation when this u dash is equal to c. Now if I take this u dash equal to c, now what is c? C is the speed of light, or you call it velocity of light in vacuum. Okay, so in this case, what we are going to have is so what we will have is this u that we have, that will be equal to c plus v, and vice versa. So it is seen that velocity of light is dependent on the frame of reference. So it depends on the frame of reference. So when one frame of reference is moving with respect to another frame of reference, then the velocity that you are going to measure either in s dash or in s, that velocity is going to be added or subtracted to the original velocity depending on the direction of motion of this frame of reference. And this kind of thing, what we see here is that u is equal to c plus v. It has been observed that the velocity of light is dependent on the reference frame, which is physically not accepted if we choose this kind of situation. And so for high velocity, I mean, if this v goes clear of the order of velocity of light, the Galilean transformation is not adequate. So for velocity in which the velocity of light, the velocity of the frame of reference is close to the velocity of light, there is a need for different transformation. And this different transformation is given by what's known as Lorentz transformation. Lorentz transformation. Now let's proceed from Galilean transformation, and this is what we discussed about Galilean transformation, that we have two frames of references, and one frame of reference is moving with respect to another at some constant speed or at some constant velocity, and and in order to have the understanding of what we call as Lorentz transformation equations, which we are going to discuss in this video, we have to go with the basic postulates of special theory of relativity. So what is important here is that the postulates of special theory of relativity, which were proposed by Albert Einstein, and what it says is that the first important point is that there is no universal frame of reference, frame of reference pervading all of a space. So there is no inertial frame of reference which is pervading all of the space. So there is no such a thing as absolute motion. So this is the first important postulate of special theory of relativity. And the second important postulate is the laws of physics are same in all inertial frames of references. Or in other words, we can say that the laws of physics are same. They are same in all frames of references which are moving with constant velocity. That should be more appropriate. They're moving with constant velocity. Now, here is another important point, and that point is the third important point. So this we have discussed, that the laws of physics are same in all inertial frames of reference. And then there is the important postulate what says that the speed of light in free space has the same value. It has the same value for all inertial observers. Whether you are observing speed of light from S or you are observing it from S dash, its value is going to be its value is going to be c. So this is the important postulate of special theory of relativity. So if I have to repeat this point, what it says is that the speed of light in free space has the same value for all inertial frames of reference. Okay, so this is same for all frames of reference. Now let's proceed for the derivation of Lorentz transformation equation. That's the target that we would like to achieve in this video. So the diagram is with us. We have two frames of reference, and we have all of those x dashes and y dashes. So what we assume here is that this x and x dash, they are linear. So that the single event that's happening, say for example, this is S and this is S dash. So an event in the frame S, suppose this is S and this is S dash, it corresponds to the single event in S dash. So the event taking place either in S or S dash, it is a single event for any inertial frame of reference. Now for lower velocity, what happens? These Lorentz transformation equations, they simply reduce to Galilean transformation equations. Galilean transformation equations, and there also exist what we call as inverse transformation equations. The way we used to have inverse Galilean transformation equations, here we also have inverse Lorentz transformation equations. Now, to start with, if I assume that I have x dash, okay, this x dash is equal to some constant times x minus vt. We'll call it 1. And so I assume that my motion is along x, so y dash will be equal to y and z dash will be equal to z. And what am I going to have here is that if x dash is equal to k times x minus vt, if I take its inverse, that will be, if I take its inverse, so taking inverse, what I will have x equals k times x dash plus vt dash. All right. And now I have this equation. I have equation 1 for x dash. I have equation 2 for x. And now what I will try to do is that I will put the value of substituting value of x dash in second. Okay. So what am I going to get is, so what will happen? So x will be k times, instead of x dash, I have k times x minus vt. Then I have plus vt dash. All right, that's the case. So if I try to open it, so this is k outside. So this is going to give me kx minus kvt. And then I have vt dash. Okay, then x will be k times, this will be k square x minus k square vt, then plus kvt dash. This should be the case. So, so what I will have is for x. For x, I will have, I can change this. So this is x minus k square x, or I can simply write down it in the same way as it is. So this x will be k square times x minus vt plus k vt dash. Okay, this will be my x, and I can evaluate the two equations for t dash. I can obtain t dash from these equations. So what will I have for t dash? I will have simply kt plus 1 minus k square by kv times x. Easy, can be obtained from this equation. Okay, so we have equation number 4. Now, what is the case for my x? If I take x is equal to ct, where c is the speed of light and t is the time in frame that we have, s frame that we have chosen as s. Okay, and for x is equal to ct dash in the frame s dash. All right, so when I do that, what am I going to have? What am I going to have is, okay, I'm choosing this. So this is my x dash and this is my x. All right, and what am I choosing here is that x is equal to ct and x is equal to ct dash. So for x, what I have is it is k times x minus vt. Okay, that's equal to, that will be ckt plus 1 minus k square by kv. The two, so c is here and x is here. All right, so I have substituted for t dash here, that's from this equation, and I have multiplied it by c. So this xct and xct dash, the two quantities are equal. Because the speed of light is same in all frames of references. Now, when we will solve this, we can solve this equation and we can solve this equation for k. Okay, so if we solve this equation for k, we can have, we will have is, this is, this value of k that we will obtain, this will come out to be 1 by under root of 1 minus v square by c square. Very simple algebraical. Now let's try to find out the value of k from this equation, and what we can do is we can multiply it x minus kvt We can transform this. This is minus CKT is 1 minus K square by KV CX. And what we have uh, X is CT, we have X is CT dash. And from this equation for T, I have X by C. So this is Kx minus KVT minus C. Uh, K, K is here. Okay, for T, I would like to take X by C. This is X by C is 1 minus K square by KV times Cx. Okay, so what we have here is this C and C is going to cancel. This Kx and Kx is going to cancel. This Kv will be transformed. This will be minus K square, V square, and T is 1 minus K square times C. For X, I can use Ct. Okay, so what we have here is this T is going to go from here. So this is minus K square, V square is, it is C square minus, this is C square minus C square K square. That should be the case, right? And we can have transfer of some terms here. So let me have, so I can think of minus K square V square plus C square K square is equal to C square. Let's move from here. So what we have is what we have is this. So K square will be common. So what will be inside? It will be C square minus V square. C square minus V square is equal to C square. And so K square will be C square by C square minus V square. And we can think of 1 by 1 minus V square by C square, dividing numerator and denominator by C square. So what will be K? K will be under root of 1 by 1 minus V square by C square. So this K is going to be 1 by under root of 1 minus V square by C square, which I had written directly. So here we can find the value of K is this much. And similarly, if we make if we do the analysis from this equation, we can where is that? From this equation we can have a relation between T dash and T. So this will be assignment for you, and you will work on this equation to get T dash, the relation between T dash and T. So what we have now, we have got the value of this K that we had proposed, and now we can write down the Lorentz transformation equations. Lorentz transformation equations. Okay, so let me draw a line here. So the first one is X dash is it is K times X minus Vt, but K is calculated, so X dash is X minus Vt by under root of 1 minus V square by C square. And along Y there is no motion, so Y dash is equal to Y. Along Z there is no motion, so Z dash is equal to Z. And this T dash will come out to be T minus Vx by C divided by under root of 1 minus V square by C square. So these are our Lorentz transformation equations, and we can write down the inverse Lorentz transformation equations. So for that, what we will have X that will be X dash plus Vt by under root of 1 minus V square by C square, and Y will be simply Y dash, and Z will be simply Z dash, and T will be T dash plus Vx by C square by under root of 1 minus V square by C square. So this is the set of Lorentz transformation equations that we have obtained when we have one frame of reference moving relative to another frame of reference. And the time that we have, the time is not playing the role of absolute. In this case, we have a correlation between t dash and t. So this set of equations that we have, we call these equations as Lorentz transformation equations. Now,